Hello friends, you may remember that we have already discussed in 3 lectures regarding controlling particulate matters and gaseous pollutants also. So, today will be the last lecture on these controlling devices, especially on gaseous pollutants. So, today's lecture contents include like we will see what we have covered so far and what we will do in this lecture. So, today's focus will be on gaseous contaminant control techniques based on oxidation and condensation. Okay. So, we have already discussed adsorption, absorption and biofiltration related devices which have been used for gaseous pollutants control or capturing, you can say, because these gaseous criteria pollutants or like VOCs and even gaseous air toxics, they can easily be controlled by these techniques, okay, like adsorption, absorption, biofiltration, oxidation and condensation. So, 3 of these adsorption, absorption and biofiltration in the last lecture we have covered. Today we will focus on oxidation and condensation. So, let us see what is the oxidation basically. So, all chemical oxidation systems are really for destroying organic compounds in the effluent gas stream which comes out of after some combustion process or burning process of the fuel. So, that is why they are used when the economic recovery of the compounds is impractical. Otherwise, we try to recover the resources, whether it is some chemical compound or something like that, right. So, the oxidizers can be used to destroy a wide variety of organic compounds, and the categories, the broad or main categories within this oxidation process are high temperature gas phase oxidation systems and catalytic oxidation systems. And these high temperature or gas phase oxidation systems can be divided into 4 main categories basically, like recuperative thermal oxidizers, regenerative thermal oxidizers, boilers and flares. And all these 4 processes can be used for controlling or destroying very high at very high gas temperature those gaseous pollutants, and they can convert combustible materials to carbon dioxide, because when complete oxidation occurs, basically what happens, the carbon dioxide, water and other combustion products are really produced by this particular combustion process or oxidation process, and it can operate at a range of temperature basically like 540 degree centigrade to 1100 degree centigrade. So, this gas temperature range is also important, because only up to that temperature if we can operate the system, then it will be able to oxidize all these kind of pollutants which are possible to burn and oxidize fully, so that it can be converted into carbon dioxide and water vapor ultimately. Well, these both thermal oxidizers or catalytic oxidizers are used to treat or oxidize effluent gases or exhaust gases, you can say, from the surface coating industry or gasoline storage industry or distribution terminals or synthetic organic chemical plants basically, right. So, there are some vapors or some those effluent gases which need to be controlled, otherwise they will go to the atmosphere and they will create several other problems according to their chemical characteristics. However, flares, burning, the flares are used primarily to treat emergency vent gases in synthetic organic chemical plants or petroleum refineries, because it is not practical to recover that. So, it is better to those vapors, those fuel vapors or fumes, to burn them directly. In the flares technology, we do that particular burning kind of process. Well, when we talk about this recuperative thermal oxidizers, you can see these in this figure it is shown like waste gas inlet at around 120 degrees Celsius, which is much colder than the system of this oxidizing system. So, it goes into this particular system and it passes through heat exchange that particular chamber where exchange of the heat is there. So, that the higher heat of those burning gases goes to this waste gas inlet, then it is again taken after this heating process. When temperature increases, it is taken around like 351 degrees Celsius, it goes to this chamber where it is burning or oxidizing happening. So, it is around 700 degrees Celsius where it is oxidized or burned, and it goes again, and then it comes out of this exit this pipe. So, the waste gas inlet basically relatively cold, this one, and then it goes to the heat exchanger system, and around heat recovery of 40 to 60% happens. So, that is another advantage, when these burnt gases pass through, then they are taking lot of heat with them. So, the heat recovery happens in this heat exchanger system, part of this particular system. At the higher temperature, when this waste gas is taken to this chamber, fume incinerator basically, so there it is burnt or oxidized completely, and then it is taken to the exhaust pipe. So, the fume incinerator is very important in that sense, and then this oxidized gases exit after passing through the heat exchanger basically. So, at the point of heat exchanger, they exchange the heat from higher temperature to the lower temperature. Well, regenerative thermal oxidizers are there, another set of regenerators. So, these regenerators is a set of refractory packed beds that store heat basically, okay, indirect way you can say. So, you can see this is heat exchanger, and ceramic media is used for this exchanging of the heat. They are first they take the heat into that, and then they keep this heat for longer period, and these are the valves to control. So, this is the particular device where heat recovery efficiency as much as 95% are possible in this particular kind of regenerative thermal oxidizers. You can see here it was only 40 to 60 degree heat recovery, but here up to 95% you can recover the heat. So, even heat when it is wasted to the atmosphere, it is also kind of wasting the energy. If we can recover the heat in the process, then it is basically we are helping the environment. Otherwise, you might have heard about heat island impact. Those things happen because of these kind of extra heat which goes to the atmosphere. The contribution is there, I mean to say. The inlet gas stream is passed through a large packed bed composed of ceramic packing, that is shown here, okay, and which is preheated by passing the outlet gases which has lot of heat from the combustion chamber and through the bed prior to the exposure to the inlet gas stream. So, that way heat exchange is possible. Okay. So, in this particular device there are at least 3 beds required for the complete process. The first one is used to preheat the inlet gas stream basically. You can see here first, second and third, all these have ceramic media and they can exchange the roll also, right, and this is the exhaust gas ultimately. Second is used for transferring the heat of the combustion from the treated gas stream to ceramic bed. So, the treated gas means the burnt gas or oxidized gas. So, it has lot of heat, right. So, that heat is taken by these ceramic bed media, you can say that bed layers is there, lot of pebbles are there, and in this this purge cycle happens in the third one and they can change the roll. So, the purge cycle is basically needed to prevent emission spikes each time the gas flow is reversed through the regenerative beds, because then beds are regenerated in that sense when they are changing the rolls. The third one is boilers basically. So, this is another alternative to installing a thermal oxidizer, and which is like burning the waste gases as the fuel, you can say, like you can see here, these are the burners and this is the gas outlet, okay, and air goes inside this. So, that way these inlet gases which are kind of we can use as the fuel and they are burnt. So, some calorific value is recovered by this particular process of oxidization or the burning, and this process and the plant boilers are normally designed to operate with the combustion chamber temperatures in excess of around 980 degrees Celsius and with flue gas residence times in excess of 1 to 2 seconds. So, within that small period, that particular heat exchange happens in that particular device. Well, flares are there, these are used for disposal of intermittent or emergency emissions of combustible gases from industrial sources which are not economical to recover basically. Okay. So, using flares to prevent direct venting of these emissions can eliminate the safety issues or health hazards which can be because of these toxic gases which can come out of these exhaust pipes. So, flares are used mainly at the oil refineries and chemical plants that handle large volumes of combustible gases, and if we do not in a controlled way, this is a controlled way of burning them, oxidizing them. If otherwise if we emit into gases at some places, if concentration is very high, then it can catch fire, or there may be other dangerous situations also. So, they can have organic compound destruction efficiency exceeding 98%. So, that way it is quite efficient way of doing away with these gases, but of course, we do not recover in that particular process, we just burn it, even we are not recovering heat here, right. Then when we talk about flue gas flow rate, like how to design those particular instruments. So, there are certain parameters which are important to know about, like the flow rate. Okay. So, the flue gas flow rate may be there, emission stream flow rate can be there, natural gas flow rate, dilution air time, air requirement, all these this emission, natural gas and dilution air time requirement, these are basically making the total flue gas flow rate. So, that we should know. This flue gas, sometimes also called like exhaust gas or stag gas, is the gas which is originated from the combustion plants and which contains the reaction products of the fuel and combustion air and residual substances. So, they are waste gases, you can say. Okay. So, we need to know these flow rates to design the particular device. Okay. So, combustion chamber volume we need to know before designing the combustion chamber. So, how to know the volume? Okay. So, the combustion chamber volume can be determined using the actual flue gas flow rate and the desirable residence time. Okay. So, residence time TR, and this is the actual flue gas flow rate. Okay. So, this is the empirical relationship which is used. Okay. Tc is here combustion temperature which is known, and then we can see, because it is in Fahrenheit. So, we can convert into Celsius. Then this Vc is the combustion chamber volume which can be computed by using this particular formula. Well, catalytic oxidation system is another way, means we have seen the oxidizing systems and then catalytic oxidation system, where catalyst the substance which accelerates the chemical reactions about the without changing itself. Okay. So, the waste gas is passed through a layer of the catalyst and it causes the oxidation reaction to proceed at a much lower temperature. That is the advantage of this catalytic bed, where we pass through the gas, okay, and it passes through this catalytic bed, and at lower temperature we can have this oxidation of these gases, then gas exit is there, right. Auxiliary fuel burners are also there, right. So, it can achieve basically this catalytic oxidizing operation system. It operates around 320 degree to 450 degree Celsius. So, this is much lower than the oxidizing device which we have seen, which operate in the range of 540 degree Celsius to 1100 degree Celsius. So, that way this catalytic oxidation system is much advantageous in that sense. It can achieve organic compound destruction efficiency even more than 95%. So, that is another advantage, and it is used for inlet concentration ranging from approximately 100 ppm to 10,000 ppm. So, that way range is also very good depending upon different industries. Well, when we talk about the flue gas flow rate, when we want to design the system, then again this is for calculation purpose, again this QE plus QF plus QD, that is emission stream flow rate, natural gas flow rate and dilution air requirement in the that same unit. So, that constitute the flow rate of the combined gas stream which is entering to the catalytic bed. Okay. So, that we can calculate by this, and we also assume that which is the flow rate of the incoming gas is equal to the outgoing after the catalytic bed. So, that is the way of calculation. Then we also know this flow rate at the actual condition. So, again similar equation is used which we have seen in oxidation, then we can calculate this volume of the catalytic system. So, that way these are the parameters which we should remember, which are used for designing purposes basically. And high temperature gas phase oxidation systems which we are talking into this particular general form, then this is the basic oxidation when we convert it into CO2 H2O basically, okay. And some if sulfur products are there in this particular fuel. So, that SO2 will also be there, and some other products of the nitrogen related. So, the gas temperature is sufficiently high, which is very important for the combustion reactions to go for completion, complete oxidation. For that we need the gas temperature adequately high, okay. So, temperature is one variable, another is turbulence, because it ensure the combustible materials and the oxygen should be well mixed. So, the turbulence must be adequate. Similarly, there is sufficient oxygen we have to ensure. So, air must be there, proper flow of the air must be there. The residence time of the combustible gases is relatively long, so that the whole system gets into this oxidation process, the completion occurs. So, the time is also issue, the time, air, turbulence and temperature, all these factors we have to ensure that they are there for the complete combustion. Then what happens, like for example, to achieve the complete combustion, the sufficient supply of oxygen goes for like this oxidation system, like methane if it is there. So, when complete oxidation occurs, then CO2 is there and water is there, water vapor is there, okay. And how to calculate the residence time? That can be calculated with the chamber volume and the gas volumetric flow rate, okay. So, V by Q, okay, V by Q. So, this is the residence time. Q, some authors use T, R, some use Q. So, that way do not get confused. This is the concept is very simple, that the volumetric chambers volume divided by gas volumetric flow rate can give you the residence time. When we see this operating principles, so in the catalytic oxidation systems, the temperature of the catalytic oxidizer is set at a level at which the controlling factor is the mass transfer of oxygen and organic compounds to and fro the catalytic surface. And we have to remember the temperature necessary for catalytic oxidation varies for the different organic compounds in the waste gas stream and the characteristics of the catalytic bed. So, depending upon the gas which we want to oxidize at the catalytic oxidation system and its temperature and other properties, we have to see those things we have to keep in mind. So, in summary we can say that this oxidation system can work for organic compounds, and it can typically the concentration range for which we use it. So, it is 1 ppm to 25% of lower explosive level, right, and it can 320 degree to 1100 degree Celsius, that can be there depending upon whether we are using this catalytic or thermal system. It can be applicable for controlling multiple contaminants, because the range of the handling with the temperature range as well as other ranges are quite larger. Applicable for control of the gas streams with the particulate matter is also in pre-treatment often required for removal of particulate matter, then it is possible to use this system. Otherwise, with particulate matters like scrubbers we could use, in this system we do not want these particulate matter, otherwise system efficiency will not work properly. So, the particulate matter with the pre-treatment we can remove and then let us oxidize the gas or burn the gas, that way the system is good for. Now, next is condensation. So, condensation system basically condensation means to reduce the temperature and recover something which is in the vapor form, so that we can convert into liquid form. So, the condensation systems is used for exclusively for the recovery of organic compounds present at moderate to high concentrations in the industrial processes in effluent gas streams, and which are of kind of valuable, means they are expensive to buy. So, it is better to recover them rather than releasing them into the atmosphere. Okay. So, there are three main categories of condensation systems based on the general operating temperature range, like 5 degree to 25 degree Celsius. This is conventional waste based direct or indirect, and condensers of other type are like refrigeration condensers or cryogenic condensers. So, they have different ranges, like A refrigeration condenser has the range of minus 45 degree Celsius to minus 100 degree Celsius, and this cryogenic condenser can have minus 75 to minus 195 degree Celsius, and for normal temperature like 5 to 25 we do conventional kind of thing, but their efficiency will vary. Okay. The most common condensers use cooling water in direct contact or indirect contact vessels, and the refrigeration and cryogenic systems are used primarily for the high efficiency recovery of high value contaminants. As I said, when they are valuable, then we have to recover them rather than releasing them into the atmosphere, because it will be economical to recover them. Well, so types of these systems could be like conventional system, as we have just discussed. So, conventional condensers are simple, relatively inexpensive devices and normally use the water or air to cool and condense a vapor stream. Okay. So, the high removal efficiencies are obtained only for organic vapors. Two basic categories of this particular conventional system could be like direct contact condensers or surface condensers. Okay. So, the direct contact condensers, if we talk, you can see this coolant is there. So, coolant kind of spray is there, and this inlet gas stream goes. So, as you have seen in scrubbers, the same system is here, and then because of temperature difference, this below dew point the vapors get condensed. So, in this particular process the coolant and vapor stream are physically mixed, that is why it is known as the direct contact condenser. If the vapor is soluble in the coolant or absorption like in water it occurs, then increasing the amount of contaminant that can be removed at the given conditions. Okay. Advantages are like they are flexible and very low cost kind of system. Disadvantage, because like mixing in the water, then it is creating the wastewater stream. Okay. So, we are converting one pollutant into another one, you can say. Okay. So, wastewater treatment cost is to be added into that system of this organic recovery cost, right. Then if we talk about surface condensers, then you can see this gas inlet is there, and these coolant outlets and this condensate outlet is there, and gas outlet is there, gas inlet is there, coolant inlet can be there. So, this coolant passes through, those surfaces get cooled, and in direct contact they do not come, coolant and this gas, because in through pipes it goes through the system. So, the coolant is separated from the vapors by these tubes kind of system, okay, tubular heat transfer surfaces. The coolant flows through numerous small tubes inside the cell. You can see these tubes are there, okay, and vapors contact the cool surface of those tubes and condense and then converted into liquid portion, and then it is collected. So, the coolant and condensed vapors leave by separate exits. You can see this coolant exit and this is condensate outlet, okay, because they have separate flow regimes, you can say, and commonly called like shell and tube heat exchanger or indirect condensers because of this process of indirect recovery. Then we come to this refrigeration system. So, refrigeration systems achieve low operating temperatures by using coolants and compressors. Okay. So, the heat is absorbed from the organic vapor laden stream, because they are hot in the this evaporation section. That heat vaporizes the coolant liquid, okay, and the coolant vapor leaving the evaporator section is then compressed, okay, and then superheat vapor stream is condensed to expel the heat from the coolant. So, that system is shown in this particular schematic diagram, you can go through, and the coolant liquid passes through an expansion valve to reduce the pressure to the level necessary for the evaporator. So, that can be controlled by depending upon what kind of vapor it is. When we talk about cryogenic systems, so cryogenic control systems use liquefied gases such as nitrogen or carbon dioxide to cool the waste gas stream to temperatures approaching the freezing point of the solvent, so that they can be condensed. So, this can collect much lower VOC concentrations than refrigeration condensers. If we compare, okay, primarily used for single compound gas streams, and to be economical the organic vapor concentration must be more than 500 ppm. Otherwise, of course, it can go for low concentration, but it depends basically. Then three general types of cryogenic systems are there, like indirect contact single exchanger or indirect contact dual heat exchanger. Okay. Indirect contact single heat exchanger and indirect contact dual heat exchanger, and the third one is direct contact. Okay. So, that way we can see this indirect contact single heat exchanger you can see in this particular system, where this liquid nitrogen storage is there and control valve, so that you can control the flow rate of this liquid nitrogen. Then it passes through this particular system, gaseous nitrogen to the atmosphere, and this solvent laden air gas goes to this, and then it condensate, because it converted to liquid, it goes down, and exhaust to atmosphere can be there, those gases. So, the liquefied nitrogen basically it flows through the tubes of the heat exchanger, while the this waste gas passes through the shell side. Okay. Then cryogenic system shell and tube heat exchangers are not well suited for the large gas flow rates and are used primarily for small systems. So, that is the limitation of this particular system. When we talk about the indirect contact dual heat exchangers, so basically this is used for overcoming the freezing problems. Okay. So, there are two chambers there. So, the liquefied gas is used in this case in a cascade type arrangements to cool a heat transfer fuel that in turn is used to heat exchanger for the organic vapor laden gas handling the system, and the capacity of the dual heat exchanger system is limited by the size of the heat exchanger, and dual heat exchanger systems are generally applicable for the gas streams like less than 5000 actual cubic feet per minute. So, that is again the limitation of this particular system. When we talk about the direct contact of cryogenic systems, then again this is similar to the this scrubber kind of thing. So, here it is coming into the direct contact, solvent goes, this particular liquid gas is there. So, it is in this particular system, then exhaust gas goes afterwards there, but the liquefied those vapors which we want to extract, that goes like a condensate. Okay. So, in direct contact system, the VOC laden gas stream is contacted with the spray of liquid nitrogen droplets. So, droplets have larger surface, they come into contact and cools down those vapors which we want to collect as a condensate. So, the outlet gas temperature is controlled by the flow rate of the liquefied gas, and the liquefied gas is dispersed using spray nozzles like spray you can see here, and in this upper areas of the contacting chamber, the chamber is insulated to maintain the gas temperature as cold as possible. So, that this condensation process is not disturbed by the outer temperature. When we want to go for design aspect, then we have to see like molar flow of this hazardous air pollutants, maximum flow rate, molar flow of the HAP outlet, then this partial pressure and the vapor pressure, system pressure, all these things you can see in these empirical relationships which are there for calculating moles of the hazardous air pollutants in the inlet emission stream, and to calculate moles of the HAP remaining the outlet emission streams. So, these are the particular relationships which we use. Similarly, the condenser heat load, if you want to calculate, then V vapor is equal to P partial, this pressure of the vapor, okay, P vapor, and this partial pressure. So, this is again estimated by using this empirical relationship, and ultimately moles of hazardous air pollutants condensed is calculated by this particular relationship. Well, when we talk about this enthalpy change associated with this condensed hazardous air pollutant system and enthalpy change associated with the non-condensable HAP, then also there are certain relationships which can be used, where temperatures and other parameters which you can know here, like T is entering emission stream temperature, T con is T condensing the condensing temperature. Okay. All these terminologies are used here for calculation purpose. Similarly, the condenser heat load can be calculated, and then you can see how much area is needed of the condenser. Okay, this condenser heat exchanger surface area, because only then we will be able to design the particular system, how much area is needed, how many tubes will be required for ensuring that much area. So, this area can be calculated by H load, this condenser heat load divided by U delta TL, and U is here overall heat transfer coefficient, and delta TLM is logarithmic mean temperature difference. Okay. So, that way you can use these empirical relationships to estimate these parameters. Ultimately, flow rate of the coolant is calculated, like this, and refrigeration capacity can be calculated by H load divided by 1200. Recovered product can be estimated by this relationship. Okay. So, in summary we can say that these condensers are very good for recovering the organic compounds, and typical this concentration range for them is more than 100 ppm, then it is efficient to recover them, and the typical gas temperature is around minus 195 degree Celsius to 25 degree Celsius as per the system, and it can be applicable for controlling multiple pollutants, and pre-treatment is required for removal of particulate matter for efficient way of working of the condensation system, so that it work only for the gas, otherwise it would be difficult or the efficiency will be reduced and system may also be disturbed. Well, this is all for today. So, in conclusion we can say that the oxidation techniques which are adopted when the contaminant concentration is significantly less and it is not economical to recover the contaminant. So, oxidation is used, burning is used, you can say in simple words. Condensation technique is used when contaminant is precious or has value, so that we can recover it, or recovery is feasible and economical. Then refrigeration and cryogenic condensation systems are primarily used for the high efficiency recovery of high value contaminants. So, that way now it is clear, I hope, that oxidation for which particular organic compounds we would like to use, and condensation for which kind of vapors or these organic compounds which we would like to use, and refrigeration and cryogenic condensation will be used primarily for high efficiency recovery of high value contaminants, so that efficiently we can recover them, because they are precious in that sense, valuable in that sense. So, this is all for today, and that way we have covered 4 lectures on controlling these controlling devices for removing particulate matters and removing gaseous air pollutants. So, this is all for today. This is the reference for your additional information which you can go at leisure time. So, thank you for your kind attention and see you in the next lecture. Thanks again.